today we will complete the completeness proof for tableaus, and next week I will do the completeness for Hilbert cell proof systems, and then if there is some time I will do some first order number theory, so that you get some more holistic picture of the application of first order theories, right? And so but I do not know whether I will have all that much amount of time to do full first order number theory. Ideally I would have liked to do Gödel's incompleteness theorem also, but that is obviously not going to be possible. Yeah. Okay. So in a certain sense all these completeness theorems for first order logic actually come from they are derived essentially from the Gödel's original proof of completeness for the Hilbert cell proof system. But anyway, we will some of these completeness theorems sometimes now can be expressed independently of Gödel's original proof. So we will proceed with this. Yeah. Okay, but before we proceed with this completeness, let us just look at an example. So let us just quickly, yeah. So these were the Tableaux rules. So you have the usual Tableaux rules for propositional statements, and then once you have Tableaux rules for the propositional connectives, these are the Tableaux rules for the quantifiers and their negations. Yeah. Okay. And of course, as I said, there is a restriction on the use of these constant symbols A. In the original work on tableaux created by Smulyan, he actually called them parameters, but anyway, we are treating it as constant symbols, but they should be new. I mean that is a property that it should be there, and so those restrictions are exactly the same as in there exists elimination in both the Hilbert style proof system and in the Kenson style natural deduction system, right. The other thing of course is really this, that theoretically any satisfiable formula. So if you take some, if I just take some unary predicate P, atomic predicate, and if I were to take Px, then for all x Px, and I consider some signature sigma, right, then theoretically what this rule says actually is that you have to take the entire set of all ground terms, and of course we are implicitly assuming that there is at least one constant symbol in the signature, okay, otherwise this set would be empty. So you are implicitly assuming that actually this entire infinite, in some order, all the elements in T naught sigma replace x to give you some P of t, right. So if you look at the, so theoretically what we are saying is that this is the tableau, this infinite path is a sort of tableau for this predicate, right. And however, of course, from an implementation point of view, we are not interested in those infinite paths basically, and that is one of the reasons why what we want to do is we want to use Tableaux proofs in a way in the same way as we use resolution. So you try to prove contradictions. And when you try to prove contradictions, basically what you are trying to do is to prove unsatisfiability. And what we know from compactness theorems and so on is that those tableaux will then be finite, and all they should be closed tableaux, and all the paths would be closed and they would be finite tableaux, and that is what you are using. But actually I do not have the time to do decidability issues, but this problem is related to the fact that validity in first order logic is actually undecidable, which means that there is no algorithm which for any formula in first order logic, which given an arbitrary formula in first order logic will tell you whether it is logically valid or not. Okay. So the net effect of that is that potentially, so it is actually semi decidable. Okay. So if it is valid, then it will find, you can find a proof for it, but if it is not valid, you do not know. If it does not, but it can possibly not terminate, and you will not know whether it is going to become valid later, right. So as a result, what it means is that theoretically that issue is related to this issue of an infinite open path in a tableau. Okay. So that so theoretically speaking, you cannot guarantee algorithmically that you will always be able to prove that your tableaus are finite and they are always closing, right, for all unsatisfiable formulas. But so that is why we use these constants essentially to direct the search on a demand basis. So we, instead of directly extending the tableau by an infinite amount, we are doing that is something that is akin to what is lazy evaluation in programming languages. We wait till a demand is raised in order to get an instantiation. Okay. And that is important, and that is actually illustrated by this example, right, where by using this constant, at this point a demand gets raised for an instantiation of the universal quantifier, and at this point another demand gets raised. So in every open place a demand gets raised, and so you sort of work on it lazily on an in demand basis. It's very similar to the implementation of lazy functional languages, where you do a call by need as different from any other call by any other mechanism. So you do a call by need, and that is what you use as a heuristic, as an important heuristic, to ensure that you get finite tableaus. Yeah. Okay. So the other thing is that in the case of propositional tableaus, as I said, your formulas are all can be once they are broken up, the original formula can be thrown away. Whereas because of this particular case, and of course whatever I say for the universal quantifier also holds for the negation of the existential quantifier. Yeah, this is the same arguments hold. So unlike the propositional case, therefore all these universally quantified statements and negations of existential quantifiers, which are the same as universal quantifiers, actually need to be reused several times. Basically each time you will come up with a different instance from this set T naught sigma. Yeah. And in order to get ensure closure of the tableau, for example, especially for unsatisfiable sets. So for unsatisfiable sets, closed finite tableaus may be constructed by basically following these heuristics. This ensures that your tableaus are so one thing is that whenever possible you apply propositional rules. So but that can happen only if if there is a formula whose root operator is a propositional connector, right. So basically what we are saying is break up all the propositional break up all the formulas which have propositional connectives at the root, and then get on to quantified formulae. And in order to ensure that you get a directed proof and needs are raised, demands are raised for particular instantiations, it is better to first apply the rules for the existential quantifier and negation of universal quantifier, so that will automatically raise the demand for an appropriate instantiation of the universal quantifier, right. And so this way you hope that you will direct the proof towards a propositional contradiction. And so here is an example. So here take this, this says that the universal quantifier distributes over arrow basically, right. And so well, only one way, I mean, the converse is not true. Okay. So if you take this, so a typical closed tableau will essentially, okay, I rewrite this formula right here. I take the negation of this formula. Clearly, now actually there is nothing to do except, now I have a choice between these two, applying a universal instantiation and breaking up this negation somehow. This is actually not of arrow, right? I mean, you can think of not of arrow as a single operator, and of course I choose to break this up by according to my heuristic. I also choose not to do anything with this because I still don't know what the demand for a term would be, right? And so when I break this up, I get for all x px, and I get not of for all x qx, and then and now it is clear this is a not of for all. So I have basically, so this step 2 being propositional can essentially be disposed of, right. So actually what I have are this universal quantifier, and essentially this existential quantifier, which by my heuristic I get not QA, and that raises the demand for universal instantiation. So which, for example, gives me this P of A, right. And given this P of A, then it also gives me this, raises the demand to initialize this to P of A arrow Q of A, which is a branching operation, is a branching connective. So that gives me not P of A, and of course there is a contradiction here, and then it gives me Q of A, there is another contradiction here, and so the tableau is closed. And so this way you sort of ensure that you get in the case of propositional logic, we were interested in slim tableaus. Here you are interested in, well, the tableau actually being finite. I mean, that's the first criterion. Slimness can come later. Yeah, that's a second priority. Right. So that's how these tableau methods work. And of course, we'll follow what we did for propositional logic in order in trying to prove completeness. And one of the things we did was we constructed, let's just briefly go through it. We constructed this notion of a Hintica set, right? And essentially, a propositional Hintica set is closed over Tableau inference. So if you look at these inclusions in the Hintica set, every subsequent application of a Tableau rule essentially gives you another member, gives you the closure for the Hintica set. Yeah. Okay. So and in fact, so one thing of course is that we had this Hintica's lemma, which said that every Hintica set is satisfiable. But the more important thing is really that you take any open path in a Tableau, just collect all the formulae in that open path, and that will be a Hintica set. And the intuition is clearly that the construction of Hintica sets essentially follows Tableau rules, which is like so what you do is, so for example, if so this is like take this Tableau rule. If you have the formula phi and psi, then you include the subformulae phi and the subformula psi also in this set. So you close it. So it's all the closures work from the hypothesis of a Tableau rule to the conclusion. So it's natural that the construction of Hintica sets therefore is essentially of preserving open paths. So if you take the set of all formulae in an open path of a Tableau, which and an open path is one where there is no contradiction, and therefore it is satisfiable, and there you will get if you take the complete open path, you will get a Hintica set. Now exactly the same thing holds for Hintica sets for first order logic, except that it is going to be infinite. Yeah. So, any Hintika set which contains a universally quantified formula is going to be an infinite set, because the set of all ground terms is also going to, instantiations of that universal formula for all ground terms is also going to be included. So, while it was possible in propositional logic to have finite Hintika sets, in predicate logic the moment you have a universal formula or the negation of an existential formula, you are going to have only infinite Hintika sets. Yeah. So, in the case of propositional logic, your tableaus could have closed paths and open paths, and everything would be finite. Okay. Here what you are going to get are tableaus which in general, if they are not propositional, in general are going to be infinite, and your open paths are going to be essentially infinite paths, except in the most trivial cases. Yeah, right. So, okay. So, what we will do is, so the notion of a Hintika set is extended to the notion of a first order Hintika set with respect to this language. So, so of course, this 1 to 3 is all those propositional Hintika set definitions, right. So, you take the propositional. So, every Hintika set has to be a propositional Hintika set, in the sense that it will be closed according to those rules of this definition, and such that all atomic propositions are ground. Yeah. Then you have essentially the quantifier rules, which say that, now this says that for any universal quantifier or negation of existential quantifier, every ground term instantiation that is possible should be included in the set, right. In the case of the existential quantifier and negation of the universal quantifier, all you are asking of course is that there should be at least one term which is ground, which should be included in it in the set, for the set to be a Hintika set. Yeah. So, of course, what happens in practice is that this may not actually be, since because of the use of a constant, this term would be some formation based on that constant. So, it is not always going to be a constant, as this thing shows, right. This example shows. So, for example, you may have to have things like FFC, for example, yeah, in the second instantiation. So there would be some ground term, and that is what a first order Hintika set has. So, then for Hintika's lemma for first order logic, now of course, in the case of propositional logic, we just had truth valuation, right. But in the case of predicate logic, you have this complicated notion of models, which are all brown color in my slides, and you do not know what kind of models can be created. It is all too complicated. The only concrete things that are available, therefore, are Herbrand's theorem. And what Herbrand's theorem gives you are essentially these concrete things, like these ground terms. Yeah. So, Hintika's lemma for first order logic essentially says that if sigma contains at least one constant symbol, then every first order Hintika set with respect to this is satisfiable in a Herbrand model. Okay, that is all you need to show. What we know from Herbrand's theorem is that if there is a Herbrand model, then there is a model. There are other models. And what Herbrand's theorem also shows is that in order to show the existence of a Herbrand model, you need to consider only the ground instances, right. So, that's really all that we need to do. So, in fact, what we are going to do is we will only look at Hintika sets which create a ground Herbrand model, and you can include the word ground here, or you do not need to include it. By Herbrand's theorem, they are both equivalent. Yeah. So, what is it? It is very simple. All that we need to do is define a Herbrand interpretation, where value and valuations, of course, in the Herbrand interpretations are just substitutions of free variables. But since we are going to only consider ground terms, so it is only going to be ground substitutions. Yeah. And we do not need to do anything really about their terms. All that we say is, so supposing you have a first order Hinticka set gamma, then if it is a Hinticka set and if it was not just purely propositional, then it would have some ground predicates, right. And if it has some ground predicates, then it would have ground atomic predicates also. That is by definition, right. It would have to be closed under all those things, right. Now, look at all the ground atomic predicates and interpret your valuation in such a way that exactly those atomic ground predicates are true, right. That is it. Once you have done that, all other predicates in the Hinticka set will be true, and that by definition of firstly by the definition of the Hinticka set, and secondly by structural induction on the notion of truth. Yeah. So, Hinticka's lemma for first order logic essentially shows that if I were to take all the ground atoms given a Hinticka set gamma, if I take all the ground atoms and make them true, and all ground atoms which are not there in the Hinticka set make them false, then I can guarantee basically by structural induction that all the formulae, all the ground formulae in gamma are true. That is their interpretation, that is it. It is a trivial interpretation. Yeah. Okay. So, then basically what you can do is you can, so you can proceed to show by structural induction on every formula that if this formula does belong to gamma, then the particular Herbrand, then this formula is satisfied by a Herbrand interpretation. Yeah. Okay. So, that is what Hinticka's lemma for FOL says, and then you have a corresponding first Hinticka theorem for Tableaux, first order Tableaux, and which is just that if let's just go back there. Okay, you remember we have this. So, this is the lemma we have just done is corresponds to this one. Every Hinticka set is satisfiable, and then there is this theorem which says take any open path of a completed tableau and collect all the formulae in this open path, and what you get is a Hinticka set, right. Of course, I proved this in terms of having sets of formulae on the path, but that was because I was using these Tableaux rules, the second form where we considered sets. We could have used the first form which was like this, in which case there would be one formula at each node of the tableau and you would just collect the entire lot. Yeah. Either way, this theorem could have been proven. Where is it now? Either way, this could have been proven, okay, and it would have essentially every open path would be would have an Hinticka set. But coming back to the corresponding theorem for first order logic, you can just prove that each rule in the each propositional rule and each first order logic rule, basically these rules and this rule, these four rules essentially create a path for the construction of a Hinticka set. And if you have universal quantifier, basically that open path would be an infinite path if you have a universal formula, right. Okay. the soundness of the Tableaux method? Well, it has basically what remember that we are not looking at. So, we here we are looking at logical validity, right. Remember that, because we have various notions of validity. If you recall, one was you have this structure and a valuation, and you are asking whether the formula is satisfied with the valuation. The next one was you have this structure and you are asking whether this formula is valid for all valuations. And the third one was that regardless of the structure, whether the formula is valid. And what I showed you, what I told you at some point was that this is what this this is the same as this logical validity, right. And what we also know is that, so we are looking at logical validity, and if it has to be independent of all these valuations and so on and so forth, then unless it is trivial, we are essentially looking at closed sentences. Yeah. So, you can think of it as essentially sentences without free variables. So, that includes pure propositional sentences without, it includes all the ground things, ground predicates. It includes propositional combinations of ground predicates. It includes quantified predicates which might have which have variables in them, but they should be closed. So, there are no free variables in them. So, you look at all those sentences, and actually all our notions of soundness and completeness are essentially of that kind. We are not taking an arbitrary, we are not taking arbitrary formulas with free variables and looking at their validity, because one thing we have already seen somewhere is that you take some formulas with free variables, yeah, let us say, and you want to prove that some other formula, let us say, is valid, is a logical consequence. What we showed somewhere was that this is valid if and only if the universal closures of these formulas are valid. Right. Therefore, for the purpose of validity, it is sufficient to consider only the closed formula, right. Okay. So, we'll assume that phi is a closed formula, and if there is and suppose there is a closed tableau rooted. So, a tableau proof of course tries to prove a contradiction. So, which means you take the negation of phi and you take a closed tableau rooted at phi. Rooted at not phi, yeah. Then every path in the tableau is closed because of the occurrence of a complementary pair in the path, and that complementary pair is of ground terms. That's what is going to happen. So, on the other hand, if phi is not logically valid, then not phi would be satisfiable, which means the tableau would not be closed, it would have an open path, right. And so, which means that if there is a closed tableau, then phi is satisfiable. So, this is a way of proving soundness which is quite, it looks intuitively obvious, which is it's sort of indirect. Yeah. Any problem? Right. Okay. And then we have a really trivial way of proving completeness. Once you have anti-cassettes, if a formula is, we are looking again at closed formula, if they are valid, then what we are saying is that there is guaranteed to exist a closed tableau. Okay. So, if there is no closed tableau rooted at not phi, let us say phi is supposed to be valid, then there exists. So, you consider any tableau rooted at not phi, there must be at least one open path in it, okay. And you consider all the formulae along this open path, they form a Hinticke set, and we know that Hinticke sets are always satisfiable, which means this not phi is satisfiable, which means phi is not valid, right. So, Hinticke sets actually give you a complete allow you to shorten proofs of these things like completeness, especially for Tableau methods. Yeah. Our proof of the completeness of the Hilbert style system may not use Hinticke sets, and it actually what we will do is we will go through something very similar to Gödel's original proof, because Gödel did not have Hinticke sets when he proved it. So, so that is something that we will look at later next week. Yeah. So, at this point okay. So, basically that is all there is for this lecture. We have proved the completeness of resolution, we have proved the completeness of Tableau, we have to prove the completeness of Hilbert style proof system. Okay. So, what then maybe I should do is firstly okay, now the important thing is that we should not take a fixed signature sigma. The sigma is a parameter, right, of your language. So, the question is, can you implement, how do you implement a first order Tableau where sigma itself is a parameter of your implementation, right. That is the next assignment. I think we have to put some deadline for submission of that assignment. Yeah. So, you implement first order Tableau, but do not take any fixed sigma. The sigma has to be variable, because I should be able to use it as a general purpose engine for any sigma provided by a user, right. And so, it is so the crucial thing in that will be the generation of this the ground terms, because you do not know what the sigma is. Sigma is a variable, right. So, you have to somehow deal with it at the level of an arbitrary string parameter that comes along with all the kinds of along with we will follow standard discipline, in the sense that unlike C language, a function symbol should have a unique arity, its arity cannot change from place to place, okay. And that arity should be specified as part of the. So, there has to be a syntax of the string of functions which allows you to take an ordered pair, a string, a function name and an arity, and an integer arity, which is consistently used. So, there has to be a check throughout the program that it is not being inconsistently used anywhere, right. So, that is one thing. So, the generation of an arbitrary term algebra where the signature itself is a parameter of the algebra, that is one challenge. The second challenge, of course, is in addition to the heuristics which we have specified. I mean, those heuristics should be these heuristic rules, of course, will be part of your engine, but in addition to that, there is the possibility that if I give a formula which is satisfiable, then you will go off into an infinite loop, right. But what you need to do is not go off into an infinite loop, and instead the moment you is to take some judgment on whether I can construct a Herbrand model for that open path, for example. I mean, that is the challenge, but in the worst case it may not always be possible, and you might actually have to consider. So, as I said, you might have to consider several instantiations of universal quantifier, and there is no a priori bound on the number of instantiations. So, it might actually go off into an infinite loop. But what kinds of heuristics can you actually create, for example, to ensure that at some point you decide that okay, any further instantiations will actually lead to an infinite path. I mean, it's no use going for that. So, what kinds of so that requires an ordering on the ground terms actually, and which by which you can take this decision. But in general, in general there are problems like occurs check and so on, which can take you off into an infinite loop. Yeah. So, this I think we should just make this the next assignment. Yeah. So, you extend your Tableau for propositional logic with a lot more code now, which it's going to be a lot more. It's just the fact that you have a term algebra and sigma is a parameter, user defined parameter, is going to make and you are going to introduce substitutions. The code is going to be much more than it was in the propositional case, and let us see what kind of an engine you can produce. Yeah. I will stop here at the moment.